Let's get started. Hi everyone, welcome to our last robotics colloquium of the quarter. No pressure. But it's a real pleasure to have Jeannette Bohg visit us today from Stanford. She's an assistant professor working on lots of amazing robotics things around multimodal learning, learning from video, simulation, grasping, and she's done some of the most exciting work in each of those spaces. She's won a number of awards, like the Early Career Award at IEEE RAS and a bunch of Best Paper Awards. And she has a really unique insight on robot learning, and I'm really excited to hear what she has to tell us today, so please take it away.
Thank you, Abhishek. Thanks everyone for coming. Thanks for inviting me as well. And yeah, today I thought of those works that I want to talk about, they all fall into the kind of bucket of scaling up data. And specifically, I want to talk today a little bit about how we work towards this aspirational goal of having robots learn from YouTube, right? Because I think just like me, many of you probably go to YouTube sometimes to learn a new skill, right? Is it crafting or repairing your car or I don't know, gardening or something like that, right? Like you're looking that up. And so it would be great if robots could do the same, right? And so I want to talk a little bit about works that we do in my lab that go towards this goal. And so why do we even want to do that? So for that, give me just a little bit of, I want to just give you a little bit of a pre-story of all of this that is about foundation models. So foundation models as a term was actually coined in this paper that came out of Stanford a few years back. Somewhere in these soup of authors, there's also my name. So there's actually a robotics chapter in this one as well, if you want to go back and look at what we thought about I guess like 4 years ago at this point. But these foundation models are really exciting because they enable zero-shot generalization, meaning that they are trained on a certain task, but then they can be used for a completely different task that they haven't been trained on. And so the way these foundation models were defined in this particular paper was that they are large models trained on vast quantities of data, often self-supervised, which is important because it means you don't have to go through the effort of labeling the data. And the important thing is such that they can be adapted to a wide range of downstream tasks. And okay, so these are stochastic models with some input and output. And of course, you know all of the famous examples like ChatGPT, DALL-E, where the input is text, and then you either output more text or an image that reflects on the text. Or you do like some kind of image understanding. Here's an ancient reference from Google, but you know, just thinking about VLMs. Or we also have models that are purely in the vision perspective, like segment anything, for example. Okay, so there are all of these models out there that are not in the robotics space. They're in areas that are adjacent to robotics, like computer vision and NLP. And what is cool, though, is that suddenly these things work, so we can actually plug them into a robotic system and enable generalization in robotics. So when I did my PhD, segmentation absolutely did not work at all. You had to do lots of tricks and do things in robotics that would never be publishable at a vision conference where everyone thought, I guess, it's solved. But you know, now segment anything actually gives you very reasonable segmentation mass, which is really exciting because it opens a bunch of doors in robotics as well. Similar with like these language models, right, that you can use for all sorts of different things. I'm sure many of you have worked on exploiting these models. We've done it for planning, for example. Or you can use feature spaces that are shared between visual features and language features. Or you could even use these methods that are imagining goals to provide goal image to a robot that it can then try to achieve. Or you have like these cool object detectors that are open vocabulary. So you can ask to detect objects in an image that this model may not have seen before, right? So it's very cool that these things exist. And again, they open up a lot of doors in robotics as well. So here are just a few works in which we have used these components that are outside of robotics as a module in a full robotic system. So for example, we use them for task and motion planning in this particular work. I'm not going to go into detail on these. I just want to show you a little bit the variety of methods. in this kind of category of methods. So here we replaced the symbolic planner with an LMM and did task and motion planning. And of course, the main problem there is that an LMM outputs probably arbitrary garbage sometimes, as you all know. And so you have to somehow verify that actually the task plan is correct or achievable as well. So this was the main focus in this work. Or we did work on generalization through summarization. So this robot is called TidyBot, and it was supposed to clean up an apartment. In this case, it's our lab space, according to the preferences of a user. And the user would provide single examples like, oh, this can here goes into this blue bin, and this fruit goes here, and so on. And then by using an LMM, the robot would summarize these preferences and be able to also put away other objects that it hasn't seen an example for into the right space. And I think another example of how people have used, and we as well have used LMMs or VLMs, is as a reward model as well. So here in this particular work, we fine-tuned a mini GPT-4, I think, as a reward model for reinforcement learning, where the VLM would basically decide whether a task was correctly executed or not. So these are all ways on how to use these methods, models that are coming from outside of robotics in a robotic system. Just a few examples from our lab. But what I think is still really lacking is a core robotics foundation model maybe that solves this problem, which is really hard. So I think at the moment we still see that robotic sensory motor capabilities are inferior to human capabilities, right? So here's an example from about 2 years ago, right? Like this is from people at Google who did this RT2 work. This was front page New York Times News, if you remember that. And the reason why people were so impressed by this was because this robot could reason over these concepts, right? So here, the task for this robot was to pick up the extinct animal, and it could figure out among these toys, right, that the plastic dinosaur was the one it should pick up. And that was very impressive because, that we know that this is hard for human children to learn, right? And so it was cool to see a robot being able to do that. But what I want to show you also, or what I want you to pay attention to, is actually how simple the grasping action actually is, right? So it's still like a very simple pick and place task. This video is sped up an undefined amount, right, as you can see by the lighter flickering here in the neck of the robot. So this is very simple still, and I think one of the main things that we're still lacking in robotics, and it's really not comparable to the kinds of things people can do. So here's a random YouTube video that someone sent me of someone repairing an iPhone and actually trying to take out the glass, splintered glass from an iPhone, right? And you can see how interesting the manipulation action of this person are, right? Like they are using tools, they are really prying out things using levers, and it's minuscule screws that this person like loosens and all of this. Like it's a very intricate manipulation problems that we are super far away from solving. Even if we ask this robot to kind of maybe handle comically large tools, let's say, and comically large screws or something like that, I don't think the robot would be able to do it, right? Like, but here it's even more than that. It's not just tool use, it's also this precision that robots don't have. And then robots are, of course, not yet able to even do really this widespread of everyday human manipulation tasks, right? Like this is an expert human, so maybe I'm not even able to do that. But this, I would really like a robot to be able to do. So a lot of people are in the community are asking if we can also have a robotics foundation model that similarly like NLP and computer vision foundation models could actually do things that they are not necessarily directly trained on, right? And can have the zero-shot generalization, especially over different objects, different environments, different embodiments, and of course all these different tasks as well. Okay, so what is a robotics foundation model, right? Like what exactly would that be? So this is a robot I used to work with once, but let's just use it as an example. Let's say it's supposed to grasp this drill and use it to drill a hole somewhere. And so what does it have to do? It has to take all of its sensory information, pixels, maybe it also has touch sensors or whatever. It takes all of these, processes these in some way, then inputs them to a policy or to some controller, whatever you want to call it, and then sends it to the motors of the arm. Here, maybe it generates motor torques. And then it moves the arm. The sensory information changes, and the whole cycle has to repeat, of course, right? And maybe there's also a task somewhere, which I forgot to put in here. Okay, so this is what the robot has to do. This whole cycle has to run like all the time, like in the millisecond range. And so what's the robotics foundation model here? It's basically this policy, right? That's what we want to have. Okay, so a robotics foundation model should be this policy. So here's again this definition from this paper that I already brought up earlier. And so how can you learn this policy, right? So one is you could do it through dynamics modeling, or how people call it now, world modeling, right? Like it's just another term for it. And that's a function that takes in actions and past observation and predicts future observations somehow, right? Like that's a world model dynamics model. Or you could directly learn the policy, take an observation and a goal and output an action directly. So these could be ways on how you implement this foundation model. And so another way is to do inverse reinforcement learning, to maybe learn, given observation and actions, a reward function, right? And then you learn, have either an optimizer or a reinforcement learning method to learn the policy given this reward function. Okay, so what is different between a robotics foundation model that you may implement in any of these three ways, for example, and a foundation model in the area of NLP and computer vision? And I'm going to just give away the answer, or at least my answer. It's like dependent on actions, right? So in robotics, you really want to, or you need the data that actually contains this action label in some way, right? Like in some representation, you need some kind of action label there. And that is really hard to get, that scale of data. So I would say if you wanted to do robot learning, the biggest bottleneck right now is this lack of data. And so here is my version of visualizing this a little bit to just hammer it in a little bit, what the scale difference really is. So here you have this bar plot with the size of the training data set used in NLP. And you see it's like trillions of tokens, 15 trillion or 6 trillion tokens. And then you have the tiny little lines that are not even up to scale that indicate the robotics data set size, right? Like 130 episodes for this RT1 data set, or 70K episodes for Droid, which was also partially collected here at UW, right? It's minuscule, minuscule, minuscule. And okay, in this comparison, I'm also equating one token with one robot episode, which might be a little bit limping, right? Limping comparison potentially. So you could argue like there's maybe a different translation, but the scale factor still is pretty bad. Here's an example from Kevin Black's talk from a workshop at Coral. He's from Pi. He made like kind of a slightly different translation between tokens and words based on time, or the amount of time that is in these data sets. And so he compares kind of the data in robotics that is out there using these circles. Yeah, so this just should hopefully for you visualize that in robotics you have like this minuscule amount of data. And then also robotics is a very much harder problem than NLP, right? So probably we even need more data than is available in these language models at all.
Can you, I mean, as a roboticist, I agree that every other problem is much easier than the problem that I work on. But can you elaborate on that? Like, what is your insight around robotics and NLP?
So of course, like, I mean, actions nowadays in these new models, they are discretized because I think not because this is a good choice, but because that's how these architectures work, right? Like for language. So I don't think that's really helping with precision, for example, with these kinds of tasks that I showed before with the phone. That's one example. The other thing is, so I think this, the fact that we have continuously valued actions, for example, in robotics, it's very different from the kind of text that we want to output in natural language or even computer vision is like images with discretized color values and all of this, right? The other thing is, of course, you want the physical world reacts in a very stochastic way. So there is just not this kind of, this, when you produce words, there's not this immediate feedback that failed, or it's like if you really wanted to succeed at a task, to, for example, pick this up, it's like a much harder problem where you have to retry and go again. So the physical world is very stochastic and difficult to handle as well compared to you outputting text. So yeah, these are some things that come to mind as well. The input data is also much more high dimensional. Right? The rules are not really clear. Again, this goes back to the physics world, as opposed to, let's say, games like chess or Go, where you have rules defined, you have discrete action spaces, and you have full state observability as well. Yeah, so I think these are some aspects. Did I miss anything? Would you add something to it?
I mean, one of the things that I was wondering was, like, if you gave something like Llama 3 the same amount of data that Pi has, how would it perform? What would it do? Right? I mean, I understand
it's still doing text. It would still do text, but you just give it less data.
I mean, like, it's a testable hypothesis. I mean, I guess like the challenge with data is also the fact that, like, it's the quality of the data, and like you can get a lot of data of like people picking up coffee mugs, but that's sort of boring.
True. That's true, yeah. I come back to that later. For example, in the Droid dataset, what's the distribution of all the different tasks? It's mostly pick and place, spoiler alert. But yeah, but if you were to train this model with less data, I mean, my hypothesis is that it would just not do as well in all of these benchmarks that actually exist for this space. That's what I think. And then the other thing is, you make a good point about data quality, right? I think it's probably easier to get good data for text than for robotics, right? Like, and then also the diversity is much easier to capture as well. The space that you have to cover is just much bigger. I think maybe that's my main argument, right? Like, just the dimensionality of the problem is much higher. Yeah. Okay. So that's with the limping example. You can find other translation of this. I think Brad Adcock has like an interesting, even more limping comparison between the CEO of Figure, if you want to go on Twitter, between tokens and robot data. But anyway, I think what I want to bring home is, like, if you wanted to increase the size of robotics data to the same, just saying that it was actually the same hardness, the two problems, right? Like, if you wanted to bring up to the same space, you would need to do Droid times 15 million, right? So I don't know, who in this room has collected data for Droid? Would you like to do more? Just curious. Anyway, so I think it's like pretty not very pleasant, I would say even impossible on real hardware. And again, I think the problem is also harder. You would even need more.
Does this number change if you're like fine-tuning VLMs? Because that already has some portion of the complexity in there, right?
Yeah, that's a good question. Yeah, that is completely not left. That's not in there in that comparison.
It's hard to know, I guess.
Hard to know, but I mean, there's certainly some evidence that if you have a VLM in there, that you need less data. But I still think, even if you, let's say, fine-tune with like robotics data instead of training from scratch, you can probably, from my experience so far, you can probably generalize much better over different objects in the same, let's say, category of a task, over different environments in the background. But what really doesn't work is the generalization over different actions, right? Or different embodiments. So I don't think that right now, I'm sure many of you are familiar with the Oxy dataset that I'm going to mention later as well, where you have like many different embodiments pooled together, data for many different embodiments. I don't think that right now anyone knows how to get tasks that are done on one robot be done on other robots reliably. And I'm not talking about pick and place, right? Like, I'm talking about like a little bit more complex robots. So this, I think, is not working. And that's, I think, where we need this data. my hypothesis, right? Anyway, so you all know Droid, right? You've met, like I see at least 2 people have gone through the pain of lugging this robot to their apartment or wherever, and then collecting a lot of data. But what I think what is really cool about this project, that so many different labs and institutions actually came together and did this effort together. I do think it's very cool that this actually happened. Yeah, I mean, 70,000 episodes came out. It's a very challenging data set. It's super diverse. It has like all of these different viewpoints. And I think it's still, the judgment is still out there. But yeah, so in case you haven't done it, this is how it looks like when you teleoperate this robot and try to collect data. This is Jimmy Woo. Yeah, he is really good at teleoperation. So you see him here in his apartment emptying the dishwasher with this robot. Sometimes, the plate is even slipping out and he has to regrasp. And here are some other tasks that he has done. And this was the platform that basically had to be moved physically between places. Yeah, so this is how this looks like. And it generated this data set of unprecedented diversity, really. So here's just this visualization of all the different viewpoints that are in this data set, all the different end effector positions that were, I think, plotted here at significant events compared to all these other data sets that are out there. Sorry. And then here you have like all the different environments. So it's much more diverse than other data sets. And here are all the different verbs that were collected, and you see here, this is a log scale, right? And place, pick, remove, these are like the most common actions that were done. So, okay. I don't want to spend too much time actually on this data set, but I just want to mention or remind everyone, in case you're already very familiar with this paper, or if you haven't seen it, that how we actually learned with this data. So we used this data set, this huge 70K episode data set, and small data per test scenarios. I think, was UW actually involved in the test scenarios as well?
No, only data collection.
Yeah, so we also weren't involved in the test scenarios, but this is basically in different places that for one particular task, demonstrations were collected. And then you would basically do co-training, means like mixing of data from these small test scenarios with the Droid data set and then train a diffusion policy. Okay, so this is how this was done, right? Like, so you always still needed data from the particular task you're actually evaluating in or interested in having the robot do things. And I'm not going to show the results, but basically what they showed is that, okay, if you do this code training, it can do better out of distribution, to some extent, out of distribution execution of these actions, for example. Okay, so that's what we did here. And that's how, I guess, we all tried like these 13, I don't know how many labs, but from 13 different institutions, tried to scale up data, right? And now imagine you do that times 15 million. Just think about it. It's like doesn't seem very feasible. So what are other strategies on how to scale up this data? So here's another one that I already mentioned, right? Where people just also did this huge cross research labs and institution collaboration, where they just pooled data together from 22 different embodiments, 60 different data sets, and ended up with this huge OpenX embodiment data set, which is has like a million episodes essentially. And this is a very interesting way to do it, but it also comes, of course, with its own challenges, right? Because as I just said, like how exactly can one robot learn from another robot on how to do a task if their action spaces are not necessarily aligned, if their kinematics are very different, if they have a different gripper especially? That makes a huge difference on what the strategy can be that you actually use. So that's like the challenge with this. And I think what was done by Pi, this physical intelligence company, with this Pi Zero model kind of shows some really promising steps in the direction of actually exploiting this data set. So you see the OpenX embodiment data set is up there, right? So they use that with their own data that they collected at Pi on all of these different robots. And then they do some kind of post-training, right? Like on some really high quality demonstrations on these other tasks. And then they can do all of these different tasks. So I think we tried a version of this Pi0 model in our lab that was fine-tuned on the Droid data set. And we found it to be very surprisingly good at pick and place, stacking, inserting, folding close, and all of this, which is all like data it has seen a lot of. But we didn't even execute it on the Droid setup. We executed on a different Franca in a different spot in our lab that has never been, data wasn't collected in the spot either. So it worked actually really well. To my surprise, because you probably all know, I mean, you should never believe, you should be very skeptical of videos, right? Like anything you see on Twitter, right? Like, like things can be, made very favorably looking, but I think it's very impressive to download a model like this and run it on your own robot with new objects with a background that it hasn't seen before on tasks that you're just typing in without collecting any data. So I thought this was very impressive, and it's kind of a step forward from, you see like now you don't have to collect specific data for a particular task anymore and fine tune on that. It seems to be much more general than this, which I thought was very impressive. Okay. But it's still, you can still easily break it. It's still very easy to break it. And I think we're not yet there to, do any task in any kind of environment. And I think here's some more ways on how people try to scale up data, right? Like this, you've probably also seen, this is this universal manipulation interface from Sharan Song's lab, where they have like this handheld grippers. And that's, of course, way easier to transport around than a full robot. It's, they basically collect this data. They have like this GoPro or iPhone here on the wrist. And then they can train a diffusion policy on it, and then this robot basically tries to do the same thing of, in this case, cleaning this plate. Okay, so that could be another way, versions of this on how to scale up this data and get this data, because clearly, I think personally, from my experience with this model and trying it, I do think it's very promising to scale up real data in some way. Okay, which brings me to other ways on how to scale up data. We could, of course, also use simulation, right? I think I had already a bunch of conversations today where people asked me, what do I think about simulation? And personally, I'm like, every time one of my students touches simulation, everything takes 2 times as long. And sometimes I'm just like, maybe we should just use a real robot all the time. But I do think simulation has its place, and there's probably a lot of scaling up we can do without spending this painful robot time, and instead spend painful simulation time. But I think simulation has a lot of limitation when it comes to specifically these scenarios, right? Like anything deformable or granular material or things like dough. These are things that are really hard to simulate, so it takes time to simulate, and the sim-to-real gap is really large. And of course, even if you don't go in this realm, if you want to scale up simulation, you have to somehow create all these assets and go through this maybe either manual or procedural generation and train robots in there. So it's, in my experience, it's still very painful to do. And
question about progress. I mean, you mentioned that the Pi0, Pi0 model was surprised you. What are the quantifiable ways in which you can articulate that surprise?
Okay. I've seen what it could do in videos. And again, I don't really believe videos. But again, downloading a model onto our robot in our lab space and let it run on a camera setup that was completely not optimized for this system, but was actually done for my students' RSS paper. I thought this was really impressive.
I guess like that's an emotional response.
That's true.
Yeah, but I'm
I'm
seeking guidance on what you think might be the right ways to quantify it. Like, and whether
metrics?
we are sort of aligned on that.
Yeah. So I think you could now set up like benchmarks, for example, right? Like, so you could look at, let's say, the droid verbs that were there, and just define a set of objects maybe that you want to either pick and place, insert, or stack, or maybe you have a bunch of clothes, right? Like you want to fold or something like that. So you could define that set and then actually quantify it and maybe compare it with whatever these other VLA models that were there before, OpenVLA, Octo.
Like a percentage success on tasks drawn somehow through some distribution on these verbs.
Yeah, and so the distribution I'm saying is like the droid, let's say the droid distribution, and then you can of course adversarially test it as well, which we've already done, right? Like that's why I'm saying like you can still easily break it.
I mean, I think like guidance on that is valuable, right? Because like I mean, you have a number, and then you want that to be 15 trillion, but I guess we want to know the plot between adding data and like truly measurable progress, right? Because that could be monotone, that could be non-monotone, that could be exponential. I guess like that's where I think
that's true.
More guidance would be valuable.
I don't think even in NLP maybe necessarily people know. I'm actually not sure. I'm curious, or maybe someone can say, like in the NLP or computer vision area, do people know what kind of data they should collect and like what this diminishing return is maybe?
I think there's widespread alignment on what matters and how to test what matters. I mean, I know we talked about it in driving also.
In this area as well.
I guess like I also agree that those areas are much more specialized sometimes than like building Rosie the robot.
Yeah. So okay. So we can discuss about benchmarks, which I think we need, but nobody ever knows what this should be. And actually, I'm thinking we should have like another kind of DARPA robotics challenge. I don't know if DARPA needs to organize it or the VCs who are funding all this humanoids stuff should maybe organize it. I don't know. But we need something like that where an external entity maybe defines a bunch of tasks and then makes this measurable. Right? That could be interesting. We could also come together as a community. We just pooled all this data together as a community, or we just collected all this droid data as a community, but have we defined a benchmark? Not really, right? Like, so we could do that as well.
I mean, I guess like I'm contrasting the desire to reach 15 trillion episodes with the desire to reach some level of performance, right? And presumably, like, one is a proxy for the other, but maybe that can be attained with 5 million episodes, or maybe that needs 72 trillion.
Yeah, I know, like it's very much a proxy. I agree. I think I'm also, maybe one more thing is like, I'm not saying we should necessarily do this, right? Like I'm just saying like if you think about, if you are now bought into the thing that you have to collect data, then here's just the amount of data that is actually available in other scenarios, and you will probably need that amount, maybe this or more as well, maybe, if you are buying into this. So just making the problem, by going into the VLA world, that's what you're buying into, and you have to think about it. So now it depends, right? Like if you want to build a robot that can zero shot, literally like a person come and like do quite a range of tasks without any guidance or practice. I think that's a different problem from you wanting to teach a robot like some very specific tasks. Right? So maybe that could be easier, and maybe would actually need much less data, right? But so what I'm saying is like the scale also depends on what you're trying the robot to do, and that's why I think maybe someone external should come in, or the community as a whole should come in and define these tasks that they think would be valuable to achieve, to measure again what we can actually do right now. Yeah. Okay. cool. Half an hour over, and I'm not even at the meat of my talk. Anyway, so I think one interesting way and promising way that I think could be out there to actually get more, especially real-world data, is to learn from videos like those, right? Like, because videos, there are definitely way more videos out there than robot episodes. And yeah, what if we could tap into those, right? So I think videos, of course, this idea is like out there already for a while, and people have tried to learn from video demonstrations. And here are a few ways on how people have tried. And like here's like one version. I just picked random examples, but I know there's like way more work out of there in this space to just categorize this work. So here's like one way where actually in my group we used activity classifier trained on human videos as a reward function to train a robot. So this was a work where I told my student this is not possible, and then he proved me wrong. But it was quite interesting. We used a 20 billion something data set, which is like just a close-up of a human hand doing different tasks. And this activity classifier was trained on this to take in a video and say whether this task was actually performed or not. And we used the same on videos that were actually rendered from a robot. So this was like simulated videos. And it worked quite well to learn what we here called manipulation concept, but you could think of it as a multitask policy as well, or a generalist policy, or maybe a VLA. Nowadays it would be called a VLA, I guess. So that's one way on how people use human video demonstration as like a reward function. Then there's a lot of work out there that tries to use data sets like the Ego4D to train or pre-train visual representations as well. And that, of course, gives you a lot of visual diversity, kind of maybe from this egocentric viewpoint that you want your robot also to be in. So that's a style of work that has been done. And then there are a lot of works that take these videos and really try to extract all the information from it, like hand data, object trajectories, all of these types of things. And here's just like one example work from this. And so today I wanted to talk about the style of work, this work done in my lab that is kind of following this idea of extracting really human hand trajectories from these videos, for the purpose of making learning from, making basically scaling up scaling up data to do robot learning as well. Okay, so I want to talk about 3 works. Let's see if I'm going to get through those. This is one work is called motion tracks, where we represent the actions between slightly differently than what you might what we usually do in robotics, but that turns out to be good to transfer between human and robots. And then I have a work that I want to talk about that basically replaces the human hand in training videos with the robot hand. And I have some work where we, yet another work that uses a single human demonstration and then creates a digital twin of the environment in which the human has demonstrated the task to then train the robot to do the same task again and then do sim to real again. Okay, so let's start with this first work. So here, and this work is called motion tracks. And basically what we do is we record human demonstration like in the top row there. Sorry, there's like always this flickering. And then want to reproduce the same task on the robot here. And you see the motion tracks are actually the motion of these key points on the human hand that the robot is then supposed to imitate and follow. Okay, so the key idea is that these motion tracks of a hand on a 2D image are transferable across these 2 embodiments. And so what do we do at test time? We predict motion tracks from the end effector in an RGB image. And in fact, we do it in 2 images and then triangulate the points into 3D space. And then we solve for a rigid transform between the current end effector and the predicted point which can then be used to find the next end effector position. Okay, so why would you use motion tracks? And I think this is true for the two first works anyway, but here's an example that we showed with motion tracks. So let's say you have robot demos that are closing a drawer to the right of the robot. And then you have human demos that contain both, closing a drawer on the left of the human and on the right of the human. So if you now only train a policy on the robot data that only knows how to close a drawer on the right, it won't be able to close this drawer to the left side of it, right? Because it has never seen it. Now, if we train on both of these data sources, the robot is actually able to do it on both sides, right? So this is just a toy example of how, with very few human demos that are just easier to collect, and training on both of these data sources, we can get this bigger diversity. Yeah.
So the human hand looks like a roboticist human hand, you know?
Yes.
Does that matter a lot?
Yes.
Or- okay.
Yes. In fact, this will matter. I'll come back to this point for sure. Like, this is one of the things that is still a limitation in the two first works that I'm going to talk about. So in both of these two works, the human basically has to move in such a way that a robot can actually reproduce it, and that the mapping is easy also between the robot and the human as well, which is like, you know, like still unsatisfiable. Dissatisfactory? No, not satisfactory. So, but you know, it's the first step. It's still easier to collect data like this than to actually lug around a robot, right? But yeah. So, but then the third work is trying to address exactly this. Okay, so let's keep with this work for now. So basically, again, we now have these motion tracks, and we have this robot that is being, so this is again an explanation for how things work at test time. So we have two cameras that are seeing this robot from two different angles. These are the images that it sees. And then given these images, our policy basically predicts the motion of these key points. These are, by the way, just diffusion policies, or it's a diffusion policy that predicts forward these 5 points in the trajectories. And then we basically triangulate these points, assuming a known extrinsic camera calibration, and solve for the 6 DOF pose. And here's like a little bit of a more geometric visualization of these two viewpoints and how we triangulate and then resolve for these robot actions. Okay, and so we are running this in the loop, right? So here you see basically this more long horizon task and how the motion tracks are basically being predicted for a horizon of, I think, 8 actions or something like this. Yeah, okay, so we collect a robot data set where we have RGB images from both images. We have the end effector positions projected on the camera plane. I don't know why it says pane. Sorry, that's a typo. And we have also know when the grasp actions are happening, right? Like there's like this green bar there on top that indicates when the grasping actually happens, which is easy to detect for a robot, of course. But of course, we want to also learn from a human data set. And there, yes, we can record from 2 images, but we don't know the end effector position, or we somehow have to now extract the end effector position. For the robot, we of course have proprioception, but for a human, we don't have that. And we need to figure out when the human is grasping as well. So what do we use to actually track this hand? We use Hammer. Today I learned that actually AR Toolkit on the Apple iPhone is better than a Hammer, which is very good information. So this is kind of how this looks like, right? Like we basically take these images and work pretty well as long as there are not a lot of occlusions and all of this. And then for detecting when a person is grasping, we are basically using these fingertip position and some mask of the target object, and there's some heuristic that is pretty simple to basically decide when the person is actually grasping. And so this is how we get this human data set labeled in the way we want. Okay, so just an overview of the method. So now we basically have a little bit of robot data that we get by teleoperation. Then we have this human data that does the same task in the same environment. And both of them have these key points annotated that are corresponding to each other. Right? So now one problem is that the robot hand is slightly differently shaped than the human hand, even though we make them look like a roboticist's hand, right? And so we have to actually train a key point retargeting network that kind of disturbs the robot key points and makes them look more like more noisy or like human key points. And then we train this motion prediction network, which is basically a diffusion policy that predicts these tracks in 2D. So we get like, again, these tracks out, and we get for 2 images, and then we get also a label whether grasping is happening or not. Yes?
Were there any examples of rotating the hand in this case, or the robot hand?
Good question. Yeah, so maybe to some extent, maybe in the image plane, because for sure the hand tracking is the bottleneck, right? Okay. So if the hand tracking is bad and can't deal with self-occlusions and all of this, then you basically can't use this data as well. And the other thing, you could get the key points, right? Because Hammer has used this Mano model internally, right? Like, so even if it's rotated, you still get the key points, even though they are not visible.
I see. Okay.
Yeah.
That's good to know.
Okay. Okay, so here's kind of the most important experimental result, which is a lot. So I'm going to break it down. So first off, here we compare to using robot demos and training just a diffusion policy or this action chunking transformer on it. It's just 2 imitation learning policies. And you see the success rate, essentially. And so here we have plotted the number of human demos on the x-axis against the number of robot demos again. And so maybe to pick out the most important take-home here is like, if you use basically, you can achieve the same success rate with like quite little, maybe 30 robot demos, but 70 human demos that are way faster to collect, right? So you need like many minutes of robot demos, but you can, to achieve the same success rate, or you can just collect very few robot demos, mix in very easy to collect human demos and get like the same success rate. Make sense? Okay. So this is the first work I wanted to talk from. So we can now learn from humans, but there's like a bunch of limitations still that we just talked about, right? Like you still have to move like a robot, behave like a robot. But one thing that you definitely still need is you need some robot data. Also, the robot data and the human data need to be collected in the same space, which I haven't written down here, but that's another limitation, right? And so we actually resolve this in this new work that we submitted to RSS this year. So this work is called Phantom, and this one really enables using only human videos to train a robot policy. And you can also collect this human data anywhere where you want. You really only need your arm, your hand, and an RGBD camera. And we really also compared this to all the other work that is kind of out there. And there's like very few that don't need any robot data. And then they are often object-centric, so they need some kind of object tracker, actually. Or they are not closed loop either. Okay, so the benefits of this method, it's like very easy if you don't need a robot at all to increase data set size and diversity. You can deploy the policy zero-shot on any robot capable of performing the task, and it's very simple. So this is some examples of how the data looks like that we collected. You see it's still a roboticist's hand. Yeah, so I come back to that point. So we have these human videos collected outside, inside, in many different rooms. And so now we take this training data that we collected, and we use Hammer to get the hand pose from this person. And then we use an inpainting method that works surprisingly well to just basically delete the human hand. We could even use, we also tried this, by the way, with OpenCV, crummy inpainting. The method works equally well, to our surprise. And then we can just use our knowledge of how the robot that we want to use looks like, what the kinematics are, and so on, to actually overlay the virtual robot by having established some correspondence between the human hand and the robot hand as well. So and what we get is an edited data set that instead of the human hand now has all robots in it. So this is how this new training data looks like now. It's basically the same videos, but with a robot overlaid. And so if you look very closely, you can see like some, let's say, not so realistic contacts between the robot and the objects, but overall it looks pretty good. It looks pretty, if you don't pay a lot of attention, I don't think you would see that this is not a real robot. And the cool thing is also you can do it with any robot that you may have. So the only thing you need to know is basically how that robot you are interested in deploying the policy on basically looks like. Okay, so now we have this new data set that is edited, and we can use it to train an imitation learning policy. We just used diffusion policy. And then we tested on the robot where we overlay the virtual robot, which honestly we figured out later is not necessary to do, but it was kind of like a safe thing to do before the deadline. And then we run the policy on this. Also, this is very fast. This is just rendering on your graphics card. And so, yeah, this is how this looks like on out of distribution scenes. So this is on in scenes where it's either like a very different surface or it's outside on the on the field behind gates. There's like people eating in the background or just cars going around. And here's some of the in-distribution scenes for a task that we collected data for.
Jeannette, what is
Yes.
the success rate of just replay?
Of just replay.
Yeah, same scene, just replay.
Right.
Then we can understand like the value of imitation.
Yeah, we haven't done that part. Yeah, I think it would probably, so replay would be you take one demonstration and then you just play it back.
That gives us an idea of the fidelity of the demonstration
Right.
and the fidelity of your transfer.
Yeah. So probably if you leave everything the same, right, like in the object is in the same place as this demonstration, it would probably work.
But you mentioned that like sometimes the hand doesn't close,
Oh,
the arm is in different
yeah.
places.
Okay.
hammer
So
error
I
and
see.
all that.
You want to know this. Yeah. Okay. So we did like not exactly this experiment, but we did want to know what happens if you train an imitation learn policy on the same amount of robot data, and then you compare to the amount of human data that you have, right? Like, so you have like, I don't know, 50 demos collected in the way we did it, and 50 demos collected on the robot. We train an imitation learning policy. What's the success rate? And the success rate is higher if you only use robot data, because it's still much more precise. Because here you are inheriting all the noise from Hammer, for example, and also the mapping between the human hand and the robot hand. So it's definitely less. But the interesting thing is, like what we did here, right? It's like we only used this edited data to train the imitation learning policy, but we also have an experiment where we say like you don't have to do that. If you do have some robot data, you can mix that with this data and just get more diversity, basically, in the backgrounds and the kind of objects you have, surfaces, and so on, without having to collect it on the robot. So we have that experiment in there as well.
I guess the point being that like if the value of this method is the ability to generate synthetic data, then I would want to test the quality of that synthetic data without the confine of pushing it through an imitation learning policy.
Yeah, and I think there will be some noise because just of the hand tracking method. And again, we tested it a little bit different than how you suggested. But of course, it would only work for the same position of this object and all of this. Yeah. So there's definitely some noise in there. It's definitely not as good as still like real robot data.
Understandable. I'm just like, again, like trying to figure out how to quantify that.
Yeah.
A clarification. In this, you have videos of human hands doing a task, and you're inpainting a robot. How are you getting the action for the robot?
We track the human hand, and this is Hammer, so it gives us there are some details there. So this is recorded with an RGB-D camera, and so Hammer is only working on RGB images, but of course in the viewing direction there's a lot of noise on where the human hand actually is. So we use like depth information to basically get like an absolute position that is more accurate of the hand. And then we have hand-defined mapping between basically how to map from the human hand to the robot hand as well. And now, I forget right now what we exactly did, but it's written in the paper. This definitely is brittle as well, this mapping. But that's basically what we used, and this is why Marianne here, the first author, is also moving like a robot, right? Yeah.
How do you see the feasibility of like providing different, like more complex demonstrations and in painting instead of the parallel geographer and a different effector like an Allegro hand or a hand?
Right. So if you had an anthropomorphic hand, you would still need to deal with the noise in the Hammer hand tracking, right? Like that will stay, but the mapping between a human hand and an anthropomorphic hand will be easier, for sure. But the Allegro hand, for example, is like 3 times as big as a human hand, so there are also some issues. But I think it will be easier to do that. Yeah.
For this task specifically, how many demonstrations did the human have to provide to get decent performance?
It's a good question. I forget the numbers right now. Maybe 50? But yeah, it's in the paper, but I don't know off the top of my head right now. Yeah. Okay. Okay. So this is all I wanted to say about this method. Okay. So we can learn from humans, only humans actually, which is great. So we don't need any robot data, and we can convert it to any robot as well. But as you all figured out, the human and robot have to basically follow the same strategy, right? So that's why the hands all look like a robot hand, although they're human. So that's something we wanted to address in this last work that I want to talk about today. Because definitely the robot, because of its embodiment, should probably do a different strategy for some of the tasks than a person would choose to do. Okay, so in this work, the idea is that we have one human demonstration, and so this is an example here of a video demonstrating just pouring from this jug. We again use Hammer, which we should stop using. We should use this AR toolkit with the iPhone, I guess, to extract a pre-manipulation hand pose, and we use foundation pose to get the object pose trajectory from this demonstration. And then we create a digital twin of this whole environment. We use some app on the iPhone to scan the environment and train an RL policy in this digital twin. And then we show that we can zero-shot do sim-to-real transfer on the Allegro hand. And so we did a bunch of different tasks here. So some snack box pushing tasks and pivoting tasks. So we have grasping, non-prehensile manipulation, and extrinsic manipulation. So there are these tasks on regular geometric objects like snack box, but there are also more challenging objects like this pitcher where you have to grasp the handle, or manipulating this very thin plate, which is difficult to scoop up. And we also have policies that are actually composing these different skills as well. Okay, so we take a scene scan from some off-the-shelf LiDAR scanning app to transfer the real scene to the simulated training environment in ISAC Gym. And then we train the RL policy with PPO, in this case, in simulation. And what we use is we use the object pose trajectory from the human demonstration as a reward guidance. And the pre-hand hand pose, as seen in the left image here, retargeted as an advantageous initialization for learning, basically. So that one is guiding exploration. And then during training, we employ domain randomization for parameters such as table and object friction, object mass, inertia, and so on, and object initialization, initial configuration of the robot arm, and so on to facilitate the sim-to-real transfer. And so here in these green images, the green picture indicates the current pose from the demonstrated trajectory compared to the current object pose represented by this gray or white picture. And this is what we use for this reward computation. So after training and simulation, we used a zero-shot sim-to-real policy transfer to deploy the trained policies on a real-world KUKA arm with the Allegro hand. And at inference time, we also perform pose estimation with foundation pose. And the RL policy then takes the object pose and robot proprioception as input and outputs an action consisting of a palm pose and a hand position. So this is this action A. And this action is passed to this geometric fabric controller that generates joint PD targets executed by a low-level PD controller. And that enables more smooth and coordinated motion while effectively avoiding undesired collisions with the environments. So that's kind of how this looks like. And here are some examples of how this looks like then in the real world. And by the way, all these videos are not sped up. This is all like ×1. And so you can see the robot can kind of lift up this thin plate and insert it and lift it into the rack. And what is maybe interesting, I'm just going to play this again. There is some in-hand manipulation happening as well. Right now, it kind of scoops up this plate. And again, this is all behavior that we also seen in simulation. So this is not just like happening like randomly in the real world. So here's this picture pouring again. Here's some non-prehensile manipulation task as well. And one of the interesting things here is that you see for this plate push, for example, the robot actually uses its knuckles instead of the fingertips, because if you ever worked with the Allegro hand, it has like very rubbery fingers that have like a very high friction. So if it were to do what the human did and scrape along this table, it would actually get stuck. And so in simulation, it learned to use its knuckles to push this plate. So I'm just going to play it again. You can see that here as well. So these are some examples where it's actually disadvantages. There's a disadvantage to exactly imitate what a person would do, and it's better if the robot can learn with its own embodiment on how to get this task actually done. Here are some more examples from this non-prehensile extrinsic manipulation. It looks honestly very questionable in my eyes. I have to pay these hands, so I don't know. I'm not sure how much I like what I'm seeing, but they seem to have survived so far. And then there are some, here's some of these examples of crossing the embodiment gap again. Here's like another example with this thin plate where the robot learned to actually clip the plate between its fingers because its thumb, right? The person obviously uses the thumb to do this, but the thumb of the Allegro hand is kind of weird. And it doesn't allow so easily to actually grasp this thin plate. So instead, the robot learns to use its two fingers basically to do it, which is kind of interesting. And then it's also pretty robust to different initial positions or when this object actually kind of leaves the pose. And now this whole method is also object-centric, right? Like, so we're using foundation pose again to track this object. And so we can use obviously different backgrounds. Olivia here is like pushing this plate around. We are turning on and off the light over here, there's like different surfaces here with different friction as well. All this doesn't matter. And there was one video where my students even took away the screen and like revealed the whole messy lab environment. And that is kind of the nice advantage of having an object-centric method that actually tracks different objects, because then you don't care really about what is actually going on in the messy environment in the background as well. Yeah, so we found, of course, a bunch of limitations as well. For example, the insertion angle for this plate was, for example, very hard to get right. So this is, and there's a lot of, still a lot of tracking errors, of course. So if you do rely on an object-centric object tracking method, you're also still very limited by the abilities of this method as well. Yeah, and so, so in this work, we, again, learned from humans, but we use a human demonstration in a very different way from the other works, right? We actually are interested in what's happening to the object, and we only get this pre-manipulation pose instead of all the poses along the entire trajectory. We also don't need robot data, at least no real robot data, which is nice. And specifically nice is that the robot can learn its own strategy. So the person who's doing the demo doesn't have to really do like the robot would do, right? It doesn't have to be a roboticist's hands. But I think what is still very challenging is this step of creating the digital twin and then going from sim to real and all of this. So that I'm not sure how scalable this is. But I'd love to hear also what others think or what strategies they have with that. But I personally am skeptical if we can do this well enough. Okay, so these were these three works, and I talked at length just about how we scale up data. And I think this is not all we need to do as roboticists. I think there's a lot of other things missing beyond just scaling up data collection, and I'm not going to talk in depth about this. I'm just going to give you some examples. So I think we need way better policy architectures to really squeeze out everything we can from this data that we have. And so here's just an example where we used equivariance embedded in a policy to transfer from really small objects of the same shape to really big objects. So from a rag to a comforter, for example. And here we have a work that has two action heads and decides whether to move the robot to waypoints or whether to do very dense actions. I also think we should work more on online policy fine-tuning. I also think we should think about multisensory input. Right now, a lot of work is just using RGB images, and it seems very limiting when it comes to precision. So I think we should think about that. And also, we need better hardware, just generally better robot hardware. And with that, I think I'm at the end. Today I talked a lot about, oh my God, sorry, I'm lost in my slides. 1 second. Here. So today I talked a lot about this kind of set of works where we try to scale up data collection by hopefully at some point having robots just watch YouTube. And with that, I'm at the end. Thank you very much for your attention.
All right. I think we're at time. Maybe one question. Go ahead.
So I know the whole goal of this is to be able to use videos and then be able to do something, right? So if, for example, as humans, right, I want to make a origami paper that use 1 or 2 videos, and then even when I do it, it won't get to the exact as it is, right? So do you have a quantifiable way of measuring that for a robot, or do you expect something like that within that error? It's not going to be exactly how the video does, right? Do you have some bounds of how to measure that?
And when you say your result of folding this origami swarm, for example, will not be exactly the same, are you saying it's going to be of worse quality in the video, or are you saying there are just going to be some differences?
That and also worse quality.
Okay.
Because we're not experts,
yeah.
right?
I think measuring things in robotics is hard, right? So obviously here we did a lot of success rate, right? But which is very subjective often, right? Like there are some examples, for example, in this last work that I showed where I'm like, I'm not sure if this was successful, if this was actually successful, right? And so it's very much in the eye of the beholder how we count our successes right now. So yeah, I think at the moment, the best thing we can do is probably have normal people look. This is not very scalable, but probably the best thing would be you have normal people who are not the developers in this method just look at rollouts of the method you are interested in and a bunch of baselines and then basically rank them in terms of like, oh, was this close to what the human showed, or is this doing the task, right? Like you can ask all of these different questions. So then I think that would be like the gold standard, totally unscalable gold standard of measuring actually how good something is, maybe. Yeah, I don't know if that was a satisfying answer, but yeah.
All right, let's thank Jeannette.